Welcome back, class, to today's explainer. Get ready because we are diving headfirst into a literal, mind-bending cosmic detective story today. For decades, the absolute greatest minds in physics have been locked in this desperate struggle to figure out the most extreme, terrifying objects in our universe, black holes. So today, we're going to examine the evidence, look at some brand new data, and explore a mystery that very nearly broke the fundamental laws of physics itself. Let's get into it. Right off the bat, I want you to imagine something for me. Let's say you're super frustrated with your studies, and you just decide to chuck your physics homework straight into a black hole. Is the information on those pages, the very specific arrangement of the ink and the paper, is it just gone forever? It sounds like a kind of silly hypothetical, right? But this exact scenario is the central mystery of our explainer today. Because if that information is truly permanently erased from the universe, then quantum mechanics as we know it literally falls apart. Okay, let's dive into this, because the plot twist here is wild. Back in the 1970s, the scientific consensus, which was famously championed by Stephen Hawking, mathematically argued that anything falling into that abyss is just lost. Forever, end of story. But fast forward to the 2020s, and physics has been completely flipped on its head. A brand new breakthrough involving something called the page curve proves that information actually does escape. No way, right? So how do we get from point A to point B? Well, to find out, we need to inspect the scene of the cosmic crime. Part 1. Anatomy of the Abyss. Before we can even begin to understand how information pulls off a jailbreak from a black hole, we have to understand what a black hole actually is. It all basically comes down to gravity and escape velocity. Think about standing on Earth and tossing a baseball into the air. The Earth's mass creates a gravitational pull that forces the ball back down. Now, if you throw it insanely hard, we're talking about 11 kilometers per second, it will escape Earth's gravity entirely. But a black hole, it's an object so incredibly massive and dense that it bends spacetime to an extreme degree. The event horizon is that ultimate boundary where the required escape velocity becomes faster than the speed of light. And since absolutely nothing travels faster than light, nothing can get out. Let's walk through this really quick study guide categorizing the three main types of these cosmic monsters. Up top, we've got stellar mass black holes. These clock in at roughly 5 to 50 times the mass of our sun, and they form when giant stars collapse. Down at the bottom, we have the supermassive black holes. These are millions to billions of the sun's mass, just lurking at the centers of galaxies, including our very own Milky Way. And right in the middle, we have intermediate mass black holes. Scientists are actually just now finding solid evidence for these, and they suspect they might be formed through violent repeated mergers. Go ahead and take a screenshot of this right now. These are the foundational 4 laws of black hole mechanics, put together by Hawking, Bardeen, and Carter. Notice anything familiar? They perfectly, and I mean perfectly, mirror the 4 laws of thermodynamics. For example, look at the second law here. It states that a black hole's horizon area cannot decrease. That is wildly similar to the thermodynamic law that says entropy in a closed system cannot decrease. This strange mathematical coincidence was our very first major clue that black holes actually have temperature and entropy. Which brings us to section 2, seeing the invisible. So how do you study a thing that is literally entirely invisible? I mean, if light can't escape the event horizon, what happens to the light that just barely grazes the absolute edge of these monsters? Now, what's really interesting about this is how we can finally visualize that invisible boundary. This is the famous Event Horizon Telescope observation of M87 star, a supermassive black hole. That purple circle outlines the classical black hole's shadow, and that dark spot right inside, that is the gravitationally lensed silhouette of the event horizon itself. The black hole's immense gravity acts like a cosmic funhouse mirror, bending the glowing plasma behind it into that bright asymmetrical ring and leaving that terrifying dark void right in the center. And that brilliantly illustrates an even wilder phenomenon. You see, most black holes aren't just sitting there frozen, they are spinning at unimaginable speeds. When a black hole rotates, it literally drags the very fabric of space-time along with it, in a process called frame dragging. In numerical simulations of light passing through that warped space, we see the black hole actually twist the light waves, imposing what physicists call orbital angular momentum, or OAM, right onto it. It's like a massive cosmic vortex, spinning the light into a spiral pattern that we can detect with our best telescopes. All right, section 3, cosmic collisions and clocks. So what happens when these massive spinning entities aren't just bending light, but actively smashing into other massive objects in incredibly dense stellar environments? Well, the universe can get incredibly violent. Look at these two gravitational wave events detected by LIGO just a month apart in late 2024. In October, we caught GW 241011, where one of the fastest spinning black holes ever observed smashed into its partner. Then, right after in November, we caught GW 241110. In this one, the larger black hole was spinning in the completely opposite direction of its orbit. These bizarre, mismatched collisions are massive clues for us. They prove that these black holes weren't just born together. They actually found each other in dense, dynamic crowds, like star clusters, merging over and over again in what we call hierarchical mergers. And speaking of incredibly crowded environments, remember the supermassive black hole at the center of our Milky Way, Sagittarius A star? Scientists just found a signal there spinning exactly this fast, 8.19 milliseconds. This is a newly discovered ultra-fast pulsar candidate sitting right on the doorstep of our galaxy's central black hole. Because pulsars act like highly reliable cosmic lighthouse clocks, watching how this 8.19 millisecond rhythm gets distorted by the black hole's massive gravity is going to allow us to test Einstein's general relativity in literally the most extreme laboratory in the universe. Section 4. The information paradox. Right at the edge of the event horizon, Einstein's relativity and quantum mechanics completely crush into each other, creating a terrifying problem for physicists. Let's trace the emotional 50-year struggle to solve this. In 1974, Stephen Hawking drops a bombshell. Black holes leak thermal radiation, which we now call Hawking radiation, and eventually they evaporate entirely. But his math showed this radiation was totally random. It carried zero information about what originally fell in. Fast forward to 1992, and physicist Don Page is sitting by a pool in Pasadena on his Christmas vacation, watching the Rose Parade, just wrestling with this idea. He realizes that if information is somehow preserved, the entanglement entropy of the radiation must go up, and then eventually come back down to zero when the black hole evaporates. This trajectory is known as the Page curve. But no one could actually prove it mathematically. It took until 2019 for rival East and West Coast physics teams to finally crack the math and calculate the Page curve for real. And their breakthrough revealed something truly astonishing. When a black hole is young, it hoards information like a totally closed-off hermit kingdom. But when it gets extremely old, something profound changes. Semi-classical gravity effects take over, and the black hole transforms into a vigorously open system. It literally stops hoarding and starts regurgitating the information it consumed. In fact, anything new that falls in at this late stage gets spat right back out almost immediately.
Section 5. Escaping the Hermit Kingdom.
So the crucial point is that physics homework you dropped in earlier, it's actually not lost. Particle by particle, the information needed to reconstruct it does eventually reemerge. But the incredible irony of this is summarized perfectly by this quote from UC Berkeley physicist Raphael Bousso. "We now can compute the Page curve, and I don't know why." I want you to really think about that for a second. The mathematical equations clearly show that the information gets out, totally saving the laws of quantum mechanics. The Page curve is real, but the theorists are entirely lost for words on the actual physical mechanism. They know your homework escapes the Hermit Kingdom, but they have absolutely no clue how it pulls off the jailbreak. And that, my friends, is exactly where I turn this over to you. Information escapes the abyss. But exactly how does it make its getaway? We've traced the anatomy of the event horizon, we've seen how they twist light, we've tracked their cosmic collisions, and we've mathematically proven the Page curve. But this final mechanism is the missing puzzle piece of modern physics. I'm looking at you, the students on this channel. The case is wide open. Who among you is going to be the physicist that finally solves the greatest cosmic detective story in human history? Keep studying, keep questioning everything, and I'll see you in the next explainer.